Başlıyorum o zaman. Okay, hello and welcome everyone to our a new episode of our AI Talk series. So today our guest is Ayşegül Dündar. She's an assistant professor of computer science at Bilkent University, and previously she was a senior research scientist at NVIDIA Santa Clara, USA. She received her PhD degree at Purdue University in 2016 and bachelor's degree in electrical and electronics engineering at Boğaziçi University in 2011. Her current research is focused on deep learning algorithms for computer vision. And I would like to thank you, Ayşegül Hocam, for joining us today, and the stage is yours.
Thank you. Thank you for the introduction, and thanks for the invitation and joining today. I'm very happy to be here and talk about some of my work on controllable image synthesis. So let's first look at a general overview of image synthesis. It has shown a rapid progress since 2014, and the progress mostly started with the generative adversarial networks, which was proposed in 2014. The idea is quite simple. We want to go from a known distribution, usually from a Gaussian distribution, to a distribution of real images, and in this case, images of faces. So we sample from this distribution and we set a generator. And the generator here is a neural network, and we want it to output realistic images. Therefore, we need to train the parameters of this generator. For that, we set a discriminator. The discriminator takes the generated image and tries to classify it as fake. And it also takes real images and tries to classify those as real. It learns this classification problem, and it tries to minimize the loss coming from this classification. On the other hand, generator is trying to maximize the same loss, which means generator will try to generate images that will fool the discriminator, because if the discriminator can't classify it correctly, the loss will be maximized. It takes the feedback from the discriminator, the gradients flow from the discriminator, and through this iterative optimization, they both advance each other, and the generator in then learns to output realistic images. And this main idea, it stayed the same throughout the years, but many things has changed that led to these highly realistic images in the end. Most of the changes were in the generator architecture, and also a lot of work was done for the discriminator architecture and some loss functions and optimizations and additional tricks. And today we can get those highly realistic images that are even difficult for us to differentiate. At the same time, people were interested in using those image synthesis tools for different applications. And in applications, we don't want to randomly generate images, but we want to condition it on some user-defined input. For example, it can be a semantic map. Here, each pixel corresponds to a semantic ID. And if we set our generation based on this kind of an input, then we can have a precise control over which pixel will belong to which semantic category. And if we can get very realistic images in this setting, then that would be a very useful application. Another similar approach is going from sketches to images. If we can draw simple sketches and then get realistic images, then this will also be a useful tool for designers and architects, and even for regular users like us. And this setup of going from this kind of an input is called image-to-image translation, because it has some similarities with the image structure. It has a width and height similar to an image. And there are a lot of research dedicated to this kind of conditional image synthesis. I will also share a work of mine that is falling into this category. Simply, the conditional image synthesis, we want to condition our image generation onto some kind of a user-defined input. And therefore, we need to feed this information to the generator. And we want the generator to output aligned images with this provided input. Therefore, we get the feedback, the training signals from the discriminator. Therefore, we need to also feed this to the discriminator. Now, in this setting, we don't only send the generated image and fake image to the discriminator, but we combine those, either concatenate those or feed those at different stages in the discriminator, and ask the discriminator to differentiate between the fake pair, this one, and the real pair. Now the discriminator has access to the pairs, and it will use all the clues to differentiate what is real and what is fake. And it will not only look at the realism of this generated page, but it will also look if they are aligned with the input image, because the real pairs are always aligned. Now, the question is, in this conditional image synthesis, there are many questions to improve those architectures. One is what to feed as an input here, because the input, it should carry a good amount of information so that we have a good control on the synthesis, and also the synthesis has high realism. And it should also be simple because we want its usability in a wide range. So those are a few of the questions. And also how to feed it to the generator and to the discriminator so we get the maximum benefit is another question here. One option.
I'm sorry. So this example is just for illustration purposes, right? Because the shoes in here, I mean, the colored shoes are the same shoes, right? Aren't they? Did you put it this as a representative example?
This is an example from this paper, but this shoe is actually generated. It's slightly different.
It is?
Yes.
I don't see the difference other than color. That's why I ask. It could be me. Is there a difference really between this brown colored and light brown? I don't know.
Yes, this one, for example, we can look at some lighting here. It looks, yeah, this is real, so it looks realistic. But this one is just,
okay.
It doesn't have such details.
Okay.
Ayşegül, I have a question as well.
Mm-hmm.
So you mentioned in the conditional image synthesis, you know, we need to figure out what X should be, and it should have enough information, etc., etc. But the thing is, isn't X determined by the application?
Yes.
So in other words, if I want to do, you know, text to image synthesis, X has to be text. I can't, you know, put other constraints on X. So that's basically given to me by my application needs.
Yes, yes. I meant while building the applications, we can decide if sketches are good enough, or if we want semantic labels, or if we want additionally instance labels, or do we also want to add some key points, 3D key points, those kind of inputs one needs to decide.
Okay.
In my first work, I was interested in the semantic maps, because this is a demonstration from SPADE architecture, which I will go through it briefly next in a couple of slides. In this architecture, they have demonstrated that from the semantic maps, you can generate a really nicely looking outdoor scenes. And the semantic maps are good for two reasons. One is it gives pixel-wise information. And second is it's very easy to obtain. And here you can see from some simple clicks, you can go to a really beautiful sceneries. First, I want to go through a couple of works that use this semantic information. The Pix2Pix HD, following the Pix2Pix work, this is the second one that achieved good improvements over the image-to-image synthesis, especially for the semantic maps. And in this one, they had this architecture, encoder-decoder architecture, similar to the Pix2Pix, but it was deeper, and it had an improvement architecture, and the discriminator is taking this input image in different resolution. So they had improvement in the generator and the architecture. But later, it is seen that this kind of an encoder-decoder architecture, it may not be very good for this kind of image synthesis, where we are trying to generate a full scene, because the pixel label information should be carried out all the way to the encoder and the decoder. And the image pixels should be synthesized based on this given label. And it may be difficult for the architecture to carry it all the way and also to synthesize accordingly. In this work, also another observation they make in Pix2Pix HD, another way to improve their results, was they show that the semantic labels are not enough actually, especially if we are synthesizing instances. So for this example, it may be enough because we are generating a natural scene here and there are no instances. But when we have multiple instances, one in front of another, then it's difficult for the generator to hallucinate where one car ends and when the other one starts. So they also propose to add a boundary map. Since for this kind of data sets, we have instance labels available from the instances, they found the edges where the instance ID changes and concatenate this with the semantic label. And when they feed this to this encoder-decoder architecture, they get a great benefit, especially at the borders. In the SPADE architecture, my work is also based on this architecture. They have shown that going to this encoder-decoder architecture is actually a limitation when producing good images, especially when the labels here are large numbers. Imagine having 80 or 100 classes. Then they observe that some of the classes are not actually synthesized. And they decided to feed this semantic map throughout the generator. The generator starts to synthesize from a low resolution, maybe 4x4, and goes all the way to 256. And we have our semantic maps that are in the original resolution, 256 by 256. And by downsampling those to this corresponding resolution, they decided to feed those. How to feed this information is then another question. It can be simply concatenated with the feature maps, but they have seen that that option actually doesn't provide any accuracy. And they decided to feed this through the instance normalization layer. So this semantic map, it goes to a couple of convolution layers to calculate the shift and scale of the instance normalization layer. And this has a similar idea with the StyleGAN. In StyleGAN, through the instance normalization layers, we feed the style parameters. And this one instead takes a semantic map and finds a pixel-wise style, shift, and scale. And it makes sense because we want the sky to have a different style than the tree. Therefore, by calculating those pixel-wise, we get an output where trees are scaled and shifted with the same parameters, and sky is shifted and scaled with the same parameters.
Ayşegül, can I ask a question?
Mm-hmm.
So the batch norm block also has its own scale and shift, but I guess
Yes.
that's not instance-wise, that's channel-wise. So the two don't actually interact. Am I understanding this correctly?
Yes, so this one, this can here, it has its own scale and shift. And other than that, there's a learnable scale and shift in all those normalization layers. So this one, we can use batch norm, instance norm, or other norms here. And we remove the learnable norm, learnable shift and scale. And instead, we have this adaptive shift and scale that is coming from conditioned on this semantic map.
But like in batch norm, there is one number for each channel. in the shift and scale vectors.
Yes.
And in your element-wise instance normalization in the gamma and beta that you show here, there is one number for each pixel. Is that correct?
Yes,
okay.
That's true. So with this architecture, they got those good results. But our observation was that it doesn't work very well for indoor scenes or some outdoor scenes where there are a lot of objects in front of each other. So all these works I mentioned, they use the semantic map. Semantic map, for example, will label both of these as zebras, and we will get a boundary map, but the boundary is not enough to differentiate instances. For example, with a boundary map and this same IDs, it's difficult to say this part and this part belongs to the same instances. And it's also difficult for the generator to realize that these two instances are different. Then when we look at the synthesized images zoomed in, they don't look like actually two separate instances at most places. For example, here we have stripes going from one zebra extending to the other, which harms the realism of these image generations. Therefore, in our work, we decided to use the Panoptix Maps. Panoptix Maps are also providing us the instance IDs here. So our proposal was we should somehow feed this to our generator so that the generator knows better about the instances. And this led to our Panoptix-based image synthesis work with my co-authors, and it was published in 2020. Our idea was similar to the spade architecture. Now, instead of only feeding the semantic map, we are going to also feed the Panoptix map. But those are quite different. In semantic map, there is a predefined number of classes. So if there are 19 classes, we usually have this one hot encoded vector with a 19 dimension. And if there is a person there, we set one there. But for the Panoptix IDs, there is no predefined number here because the number depends, the number is based on the number of instances you have. And for these instances, one way to be set a very large vector here and make sure that even if there are 30 instances, you have enough number of rows there. But that also that introduces computational inefficiency because we are only using some of those instances. And also instance 1 and 2, it doesn't carry any information about the style, but I only want to use it to differentiate those two. So we are going to use the Panoptix Maps, actually, not similar way in a spade, but we are going to build a Panoptix-aware convolutional and upsampling layer. And our idea in using the Panoptix map is when I am synthesizing this pixel value, I only want to calculate the features when I apply my convolution, only the features coming from the same instances. And I want to mask the pixels that belong to the other instance. And this has some similar ideas with the hierarchical image generation. Previously, some researchers, they found that this scene generation overall is very difficult, and they proposed to do hierarchical generation where they first synthesize a background, then cars, and then person. But it's also computationally inefficient to do this for all the instances you have. Instead, we are going to do a one-shot synthesis, but we are going to mask our convolutional results based on the pixel belonging to their instances. So looking at this in detail, I will have a convolutional layer. I will have a feature map here, and I will apply my convolutions over it with a sliding window. But at each point, I will go to the Panoptix map. So if I am calculating the feature for this pixel. It belongs to here in my Panoptic map. And I'm applying a 3x3 convolution. I will extract this 3x3 patch and build a mask here. And the mask will have ones for the pixels that have the same Panoptic ID with the center and 0 other ones. And this is quite easy to compute. I just take the Panoptic IDs and then subtract the ID of center. And for the ones that are equal to 0, I set those as 1. And for everything else, it becomes 0. And in this example, for example, I have this center green. And so I have 1s and 0s here. And when I compute my convolution filter, I do element-wise multiplication. And at the same time, I also multiply it in an element-wise with this mask. And I also want to have a normalization coefficient here, because I want to see if all the patches are valid, then that actually gives the regular output of a convolution. But if only very few of those valid, then I normalize the results based on the ratio of the validity in my mask. And here the idea is similar to the hierarchical image synthesis. When I am synthesizing this pixel, there may be trees behind it, or building behind it, or another person. And there will be features that will be dedicated for that semantic class. And when I am calculating the feature for this pixel, I don't want it to be affected by the other ones. And this idea of having this kind of masks were also used previously for image painting. And in image painting, it was used to mask the whole areas, because when you erase some part of image, then those pixels shouldn't contribute. And in this one, we have a different idea, different setting, where we generate those masks based on the Panoptic IDs.
Can I ask exactly what the mask is applied to? So you have a convolutional weight W, you have the input X, and then you have the output of the convolution Y, let's say. The mask is applied to W, X, or Y?
Before calculating Y. So first, when I apply the convolution, first I do patch-wise multiplications. So I have this filter, and it takes the corresponding pixels and multiply it here. And then after that, I multiply it with the mask. Okay. And then after sum it up based on this normalization.
Okay, thank you.
It can also be multiplied for the filter too, but at each time it will be multiplied. So at each time the filter will be different. The second layer we wanted to use this panoptic information was the upsampling layer. In image synthesis, we start with a low resolution 4x4 and do some convolutions and then some upsampling layers to go to the resolution that we want. And usually we use a nearest neighbor upsampling. Nearest neighbor upsampling is just copying it over to the neighbors. We usually do a 2x2 upsampling. But when we upsample these features, we don't use any information about their instance IDs. We just copy over the top left pixel to the neighboring 2x2 cell. So we look at the Panoptic maps here again. We usually, in our synthesis, we are interested in upsampling the feature maps. But here I show an example on the Panoptic maps. We are not going to upsample the Panoptic maps in our pipeline. But if you look at the Panoptic maps, we have an original resolution 256 by 256, and I can downsample it to 16 by 16 and 32 by 32. And imagine that we also have the corresponding features here, 16 by 16. And when I upsample it to the 32 by 32, it will be copying over the pixels similarly as in this Panoptic upsampling. And here we see two sources of mistakes if we want the features also to be upsampled in an aligned way. One version is we have misaligned pixels. So this one here, now it's copied over from the yellow person feature, but actually it should have been belong to the green person's feature. And the second one is the newly appeared classes. When we are generating it, some classes they are very small. For example, traffic signs are very small, and they only appear towards the end. And we don't want to copy it over a neighboring cells, but we want to fix that and generate new features for those newly appeared classes.
Ayşegül, why are we upsampling the Panoptic map if we have the full resolution in our hands?
Yes, this one is just for visualization. We are going to upsample the feature maps, but
okay.
the feature maps will have
similar problems.
Okay. Yes.
Thank you.
So here I again put the Panoptic Maps here just for visualization, but here actually we are interested in upsampling our feature maps. Here it shows a simple example of a misaligned pixel. This may be our original meaning that I go from 256 from the full resolution to this resolution, and here from full resolution to a smaller resolution. If I upsample this Panoptic map, I have this 4 yellow, 4 green. But actually, if I look at my original, this should have been yellow. And I want to do this kind of fix during my upsampling on the feature map. So instead of copying this A over, I want to, and B over everywhere, I want to instead copy this A here. Because our motivation is that this pixel belongs to this instance, therefore the features should be coming from that instance as well. And for that, we have this code, which basically checks the 4 neighbors, the 3 neighbors, and see which has the same Panoptic ID and copies it over there. And we also keep a mask, a corrected mask, which we first initialize it with 0. And then for every time we copied over a correct feature, we fill that part with 1. And in the end, we will have it full, mostly filled. But for some newly appeared ones, for example, this one, it will not find any neighbor to copy the feature from. So this will be zeros in the mask. And we are going to fill those pans in the second step. Here we want to, for this newly appeared pixel, we want to generate new features instead of copying the old feature, because if we just copy the old feature, maybe in this one, this pixel belongs to a tree, and in another one, it belongs to a sky. So at each time, we will be copying a different feature here. And since it appears towards the end, the generator won't have enough time to synthesize good instances. Instead, here we feed the semantic map through our convolutional layer and generate an intermediate feature map. And we multiply it with 1 minus mask, this one, and add it to our previously added upsampled features. Now, with this one, we have this full architecture. We feed this Panoptic map to both convolutional and upsampling layers. We also use the spade still, the instance normalization layer, where the semantic map goes to the instance normalization and Panoptic map goes through these convolutions and upsampling. After that, we look at some of our image generation results. Here we look at the FID score and semantic score as in previous works. But we also look at the instance score here. We look at generated images and took a pre-trained faster RCNN and feed those images to that faster RCNN. We have the ground truth labels. Here we assume that the detector is very good, and if the detector can detect it, then my image synthesis is also good. And we realized that we saw that with this architecture, we got a very good improvement on the detection results. For example, here we compare it with CRN, which is a previous work without using any generative loss. And this is the spade where we base our baseline. And this is our method. In this one, when the two zebras are expected to be generated, it doesn't do a very good job. It's again, the features are going from one to another. And the detector is also having a hard time and only detects one zebra. But in ours, the detector is able to detect both of them with very high confidence. And I think this example is even nicer. It shows the change in a better way. Here we have a lot of cows that are one in front of each other. And for spade, it's difficult to differentiate those ones. But for us, we even get different colors for different of those cows. And it looks so much nicer in this example. So after that, I'm going to talk about some limitations here. So in this kind of works, where we fit our panoptic maps or semantic maps, there is some kind of a control. We can control the content where each pixel, which class they will be belong to, but we can't control the viewpoints, meaning that we can take a car, for example, and rotate it around, or we can't generate a street and try to move around with our cursor. Because here the control is quite limited. One is 2D images, and we are only relying on semantic maps. And another problem here is, even if we change a little bit, the disentanglement between the identity and the viewpoint is not strict. So when I rotate an object, or if I make the object a little bit smaller in my content, try to have this zoom out effect, it will change the identity. Maybe the color will slightly change because there is no strict disentanglement. Even if I learn different styles, there's another option. You can also fill your instances with style information, but it will go through a neural network, and there is no guarantee that your neural network will keep that identity the same. Because of these problems, we again visited if this panoptic based or semantic based image synthesis is a good direction. Then with also getting quite popular these days, 3D inference, we also got interested in this topic, because with 3D inference, now you get the full control on the viewpoint or of your image synthesis, and you also get a strict disentanglement for the identity and the viewpoint. With 3D inference, I mean, there are many different ways to represent your 3D information. There's also a lot of research going on. What is a good representation? In this one, we are interested in the mesh representation. So we have a sphere with all these triangular meshes with a fixed topology. And we try to deform the sphere into an object we want. And we also want to learn a texture map. This texture map has this fixed correspondence with the vertices. So when we get this shape and the texture map, we can warp it around the object. And if we can get these two in a very high fidelity, then we are almost done, because we can change the rotation of it, and there will be the strict disentanglement between the identity and the pose, because the identity is given you by this 3D mesh and the texture. So when I look at it from here, I will see this part, And when I look at it here, I will again see this part in a slightly different way, but they will all be getting this patch from here. So I will be sure that there will be no sudden color changes or the model of the car won't change and so on. But getting those are very difficult. If we get 3D data in the laboratory settings, we scan objects and we can also get their texture maps, then it's slightly easier. But we want to be able to extend it to arbitrary number of objects and categories. Then it's very difficult to gather all this data. So we are looking at 2D images, some images that are easy to collect to get this kind of information. And this is difficult because going from 2D images to the 3D is difficult because we don't have the full supervision. We only have supervision for the visible part. Learning 3D information from 2D images has also been only recently became possible thanks to this differentiable renderer. There are many renderers in the last 2-3 years that are proposed. And among those, we use this the Ibr renderer. This one, it is differentiable because there is no hard masking here. It outputs an image here, it expects a mesh and a texture. We can forget about the light for these examples I will talk about. It takes a mesh and a texture, and it also needs a camera parameter. So first it rotates the mesh and projects it to the screen based on the camera parameter. And then it knows where the vertices are. And from that, it can sample from the texture and copy the patches over and outputs a rendered image. And during training, we calculate a loss between the input image and the rendered image. This provides a color loss, which mostly trains this texture. And we also have a silhouette loss here. Our rendered image, the projected mask, has a silhouette, and we also have the masks for this input image. And if we, for example, estimate a very small car here, we are trying to maximize the intersection over union here. The closest vertices will get more signal to be pushed outwards, and the farther ones will get less gradients for that. Or if we get a very big car, then those vertices that are responsible for the car to be big, they will get a signal to be pushed inwards. So this renderer briefly works like that. We don't need to go much in detail. It basically provides us the gradients to train our neural network, and the neural network will output a mesh and a texture.
Can I ask a question about this?
Mm-hmm.
There is this renderer which takes camera parameters as input. So do we assume that is it known a priori, or
yes,
are there ways to estimate that as well?
Currently, we assume it is known given to this architecture. So yes, this is also a very computationally heavy thing to estimate. Usually these days we have those collection of cars, for example. For synthetic data is easy, but for real images, they have this key points, and from those key point labels for many of those images, they run a structure from motion and then estimate a camera parameter for each image.
Yes, but is it also maybe would it be possible to integrate that parameter estimation task into this end-to-end learning system somehow?
Mm-hmm. Yes, so it can also receive gradients, and we actually start with some camera parameters, and this renderer is able to fix it a little bit, but learning it completely completely from scratch, it doesn't do a good job.
Okay. So in this work, for example, the work that you're showing is, it's assumed that the parameters are already known a priori.
Yes, yes.
Okay, thank you.
It also computes the gradients for that. So there is no limitation for us from learning it, but it's already a very difficult problem.
Mm-hmm.
So it doesn't learn.
Well, okay.
But
Maybe
there are some works that do some multiple camera hypothesis. So they initialize 10 different camera views, for example, and then try to optimize those, the best matching ones slightly. They show some promising results, but also not as good.
because that's one of the probably most important restrictions in this problem, that this assumption of camera parameters that we know them a priori, right? Because so that just because of the reason people mostly work on synthetic images, which in turn affects actually the quality of the synthesis results that we have, probably, right?
Yes.
Okay, thank you.
But even with the known camera parameters, actually the results are not very good yet. They are not in the generative GAN-based synthesized image level. So yes, because here another limitation we have is we are trying to reconstruct this image. So from this view, it only gets feedback, for example, for this visible texture, and it doesn't get good signals for these ones. So we will see next, it may look very good from one view, but when you turn it around, the mesh may not look realistic and the texture may not look realistic at all. And this observation led us to this work, view generalization for single image texture 3D models with my co-authors. It was an internship project published in 2021. The challenges here is there is a difficulty in view generalization. So for example, let's look at this car. It can be, it's not perfect, but it's reasonable when you render it from the same view. But when you render it from the other views, the results look really bad. And this happens for both meshes and also the textures. Meshes are squashed a bit and the textures have faded colors. And this is other methods. This one in the rotating one, you can see it's not very good. For one view is good, but for the others it's not good. And this one was also one previous work. The results not good there as well. There are a few ways to solve this. One way is to collect multi-view dataset, but multi-view dataset is also difficult to obtain. And also we need to get those camera parameters as well. So we were interested in improving this for single view datasets. In this work, we had proposed different kind of consistency losses that improves the guidance for the single view. And we also added some mesh templates to our network and controllable deformation. Let's first look at this overview of our approach. Similar to the previous work, we have an encoder and decoder to output a texture. And different than others, we used different templates. The computer graphics, there are different assets. So we used 8 different card templates here. Our network now needs to find the best template and also finds the offsets from that template to fit better to this input mask, to input image. And here for this offsets, instead of if we have, for example, 647 vertices, instead of having a linear layer that outputs 647 vertices, we output a UV deform map similar to this texture map, and we sample from there. This ideas is used before, but here we also used it to control the deformation flexibility. If we use a small map, when we sample from it, we do a linear upsampling here, then it will have more limitation to deform it. And if we use a larger map, then it will have more flexibility to deform it. During this learning the meshes, you need to put a lot of regularizers because it starts to make a lot of mistakes. So limiting the deformation is actually one regularization we put here. And we see a different kind of behavior for different objects. For cars, we find that if we have a very small deformation offset, if we let a small flexibility there, then we get better results. And that's also because thanks to the templates we have. From the templates, we don't need to move the vertices as much. But for example, for birds, if we limit the deformation flexibility, then we only get this kind of bird, and it doesn't have any variant diversity among the examples. And if we increase the deformation, now it gets better here. This is our overall framework. And we also now propose how to train this with different kind of regularizers so that we send some feedbacks to these invisible areas. The first regularizer we used was the rotation gun cycle consistency. In this one, we have an input image and we have an encoder decoder and use the camera view and output the original view. This is also the standard way of training these networks. But in addition to that, we also viewed it from a different camera parameter. So we got a novel view here. And after that, we again feed it to the encoder decoder and estimated the mesh representation and texture maps and use this same camera view from the beginning. And now we try to reconstruct the original view. So we provided a cycle consistency here. And other than that, to feed some feedback through the intermediate image, we also train a unit discriminator here, which tries to differentiate real and fake. But with this discriminator, we see actually some small improvements. It's not easy to train this framework with a gun loss because there are some limitations in the renderer, and generative adversarial networks are also known to be very difficult to train. So those improvements are very small here, and you need to tune a lot. In our second consistency, we called it texture mesh alignment cycle consistency. One problem we find is it's specialized to the given input a lot, and the texture specialized to the given input. And when it is viewed from the other views, it's not as realistic. But if they are all aligned, meaning that if they all learn the tires at the same place and the tail lights at the same place, then they won't be overfitting to this view. And from the other views, it will also output some better results. And for that, we took 2 pairs of images and encode their meshes and textures. And from that, we swapped the textures and rendered those 2 images. It used the mesh prediction from here and the input camera parameters from here. And again, from that, we encoded the texture and swapped it back. And now again, we completed a cycle here and added an image reconstruction loss between the input image and this final image we generated. So this way, here, maybe it got some feedback signals for these pixels, and now it got more feedbacks for the front pixels. And also throughout this we now encode texture for this view, but decoded it from a different view. So we force the network to learn realistic textures for the invisible areas as well. And with this one, here are some of our...
Can I ask a question at this point? So if we look at this texture map, actually this applies for like most man-made object. Symmetry is a very important prior. Are these type of approaches use that type of information, like for example, for the generated textures or maybe even meshes?
Yes, exactly. Actually, here I forgot to mention we are only predicting half of it.
I see. Yeah,
but yes,
makes sense.
Yes, but that's also a bit limit. Yes, it's also a bit limitation for the plates. So every time I have an improvement, I try to remove that symmetry constraint, but the results get really bad suddenly. So we still need this, but that's why I think the plates are not very good in those examples we have. So here we compare with this previous work, the IBR, which we use the renderer from, but they also have an architecture and their results. And our results, this is without any consistency. And the improvements here coming from using the mesh templates and also limiting the deformation. And with the consistency now, we get some improvements in the texture. For example, here only the back side is visible. So into the front, it doesn't output anything nice. But here it at least tries something. So there is some improvements here. But still there is a lot of room improvements for these results to get to the same level of those GAN results for image synthesis. In this one, we compare these methods for the mean IOU. Mean IOU, it looks at your input image and you render it from the same view and you compare the masks intersection over union. So it doesn't look the image from any other views, which is a very limited kind of an evaluation, but this one was mostly used previously. We also added an FID here. In FID, we viewed those images from 6 different views and then calculates their FID, comparing it with the real data. And with this FID, we got some improvements over the baseline here. And actually our IOU, it got a bit worse, and it may be because we are not overfitting to that given view, but we are outputting a realistic view from everywhere when you viewed it. And with that, that's all I have. Thank you for listening. I can take any questions.
Can I ask a very small question? So in this system that you were training, there were different tasks or different types of losses, even adversarial loss that you somehow incorporate. So when you train this, do you train this alternately or it's a joint training process? How do you do that?
Only the discriminator is in another iteration. But other than that, all the losses, I add them together for this, for the generator architecture.
Okay. So there is one single loss function that takes all into account. Okay, thank you.
Mm-hmm.
Any other questions from the audience?
Ayşegül, I have a weird question. How do you see this scaling up, like to the full scene? How do you think it will happen?
This is, yes.
Just
yes. Yeah, maybe one way can be one option for the scene, for the static objects, maybe it's a nerve-based model can be used. And for the moving objects, maybe this mesh representation can be used. Yes,
I guess
or
it's-
mesh representation can also be used for the behind, for anything actually. There is, these days, there are so many different representation and very different rendering techniques. So it's difficult to foresee what will happen.
It is true. Any other questions, I guess, John-Mike?
Yeah. Yes, if you don't have any questions, we can thank our guest today. Thank you, Ayşegül Hocam, for this very informative talk.
Yes, thank you for having me today.
Teşekkürler.
Teşekkürler.
İyi günler.
See you
Umarım
everyone.
yüz yüze de yaparız Ayşegül.